Hello everybody. It was in 1999 at the Probability and Random Models Laboratory of the University of Paris 6 that I meet for the first time our speaker today, Professor Hélène Guérin. I am really happy that she is one of our speakers. Professor Guérin has prepared her doctoral, her PhD thesis under the supervision of Professor Sylvie Milliard between 1999 and 2002. Between 2003 and 2019, she was an associate professor at the University of Rennes 1, France. And then she left for Canada to become a full professor from 2019 up to now at the University of Quebec in Montreal. She is a member of the Probability Lab at the Center of Research in Mathematics, CRM, and associate member of StatCam. Her research focuses on the study of stochastic processes, their properties, and long-time behavior. She is interested also in models in various fields, physics, biology, actuarial science, involving processes such as piecewise deterministic Markov processes, interacting particle systems, diffusion on manifold, random walks, and living processes. She teaches in actuarial science, statistics, and mathematics program of the mathematics department. The talk of Professor Guérin has as title on different stochastic epidemic models with varying infectivity and susceptibility. Thank you, dear Hélène, for agreeing to honor us and speak in our webinar. And please, you can start.
Thank you, Rafik. I would like to thank you for the invitation. It's a real pleasure to present today. So I will speak about models in epidemiology. Usual classical models, the infectivity and the susceptibility are step functions. And in my presentation, we will consider more general functions. So this presentation is based on two works. The first one with Arthur Charpentier and Félix Foutel-Rodier, where we have considered some epidemiological model with a vaccination policy. And the second one is a work in progress with Brice Zotza, where we consider also varying infectivity and susceptibility, but we added some memory of the previous infection. So here's the outline of my talk. I will first give some vocabulary in epidemiology. You may be used with this vocabulary since the COVID crisis, but I will recall the terms. And then I will present some classical epidemiological models, the SIRS model, and explain how we can extend it, and then introduce three models with varying infectivity and susceptibility. Then I will give the main results on the equilibrium states for those models. And in the third part and fourth part of my talk, I will focus on the last model, the model with Brice Zotza, on the model with the memory of the past infection. And indeed, it is a parametric model, which was not the case for the first model I will present. For the model with memory, we have used a parametric model because the memory is not very easy to handle. So it was quite nice to focus on parametric model. So some vocabulary, give you some definitions. So in my presentation, I will consider an homogeneous population, which means that, how can I say, all individuals behave in the same way to the disease. There is no contact matrices, there is no age effects, nothing like that. So we will speak about epidemic when a large number of population is infected in a short period of time. I'm sorry, I can't see my slide. Yeah, it's better. Then there is a value of interest in epidemiology, which is R0. You have heard about this number R0 on the news during the COVID crisis. This is R0 is the average number of infections produced by just a single infected individual in the population, completely vulnerable to the disease. So larger R0, faster the epidemic spreads. It's okay. We will speak about endemicity when the disease remains present in the population at a relatively low and constant rates in long term. And now I introduce the notion of infectiousness curve, and so I will denote it by lambda, and susceptibility curve, which will be denoted by gamma. So lambda, so after being infected, a person will spread the disease at some rate lambda during a period of time, a finite period of time, Ti. So the support of lambda will be compact. And in the classical model, lambda is just a step function, but in our model, we will consider lambda a function which will depend on the age, the duration since the last infection. And as we are considering an homogeneous population, the distribution of lambda, so there are random curves, the distribution of the lambda is the same for all individuals in the populations.
What do you mean by concentrate? The rate is R0 or not?
Sorry?
What do you mean by concentrate? Concentrate. The rate is R0 or not?
The rate, no, R0 is the mean value of the infectiousness, indeed.
Okay, and how you define the rate? What's
the rate,
yes.
I will define it more clearly later.
Okay, thank you.
Indeed, this is the force of infection of an individual. Larger lambda is, more the individual can spread the disease. And we can, there is no way to assume that lambda is equal to 0 when, so yes, lambda is equal to 0 when he is not infected, but as soon as he is infected, there is no way to have lambda that jumps from 0 to some positive value. We can imagine that lambda is a curve that will increase because when you are infected, you are not instantaneously infectious. So lambda grows slowly. And then after some days, some weeks, lambda will decrease. But there is no way to have a step function. But I will show you some picture later. And gamma is a susceptibility of an individual. So this is it. It is indeed the probability that an individual become infected after a contact with an infectious individual. So when there is a contact between a susceptible individual and an infected individual, the susceptible individual might be infected or not. And the probability to be infected is called the susceptibility. Is it clear?
Yes.
Thank you. So as for the infectiousness, there is no way to have a susceptibility that jumps from 0 to 1. Because the susceptibility, we can easily imagine that will grow slowly. So we will consider gamma as a function of the time since the last infection of the individual. And we will also assume that gamma, the distribution of gamma, is the same for all individuals in the population. So we consider a population of size n, a fixed size of the population. The size is constant in time. Initially, one proportion of the population is infected and the other one is vulnerable to the disease. And I will denote by lambda I the infectiousness of the IS individual at time t, and gamma I, its susceptibility at time t. In the classical model, we divide, oh, not 2, but 3, the population into 3 categories. Sometimes indeed only 2. But this classification is not well adapted to our model, but I'll just recall it. So there is a state I, which an individual is in the state I when he is infectious, the state S for susceptible individuals, and R for recovered individual. So susceptible, which means that the people are vulnerable to the disease, and R is when the individual is totally immune to the disease. And we will always assume that the product lambda I, gamma I is equal to 0. This means that an infected individual cannot, so if an individual is infectious, lambda I is strictly positive, and an infectious individual cannot be reinfected. That's the meaning of this assumption. So now I recall some a classical model, the SIRS model in epidemiology. And as you can see, the susceptibility in blue here is a step function, and the infectiousness is also a step function. So T represents the time, A the age since the last event, either infection or recovery. And how can we describe this model? At some infections time, here I have an infection, the infectiousness jumps from 0 to some value beta, stay constant equal to beta during an exponential time ti, and then jumps from beta to 0. The individual stay in the recovery state during some exponential time tr, So in the state I and R, the susceptibility stays equal to 0. And at the end of the recovery period, the susceptibility jumps from 0 to 1. Then it stays equal to 1. The infectiousness is equal to 0 until the next infection, where the susceptibility jumps from 1 to 0, and the infectiousness jumps from 0 to beta, and so on. And in this case, we can compute quite easily the value of R0. It is equal to beta, the value of lambda, times divided by mu, but 1 over mu is indeed the expectation of the time, the infection duration Ti. So R0 is just beta times the expectation of Ti. So as I said before, there is no reason to assume that the susceptibility jump from 0 to 1, but we can imagine a curve here. And also for the susceptibility, there is no reason to be instantaneously infectious when you are infected. And we can imagine a curve, a parabolic curve for lambda. So that is the model with varying infectivity and susceptibility. The first model was introduced by Forien, Pardo, and Brice Zotza in 2022. In this case, R0 is defined as the mean value of the susceptibility. But as you can see, if lambda of A is equal to beta times the indicator function that A is smaller than some exponential, some time, indeed, we don't need it to be exponential, we recover the previous value, which is beta times the expectation of Ti in this case. Of course, when we have a more complex curve, it's more difficult to compute it explicitly, to have an explicit form. So, Forien, Pardo, and Brice Zotza worked under some assumptions. They assume that at each new infection here, two curves are sampled, the susceptibility curve and the infectivity curve, independently of the past. So there is no memory of the past, of the previous infection. They also assume that the infectivity is bounded and indeed with compact support function. Gamma, the susceptibility is between 0 and 1, but since it is a probability, it's good to have a value between 0 and 1. And we assume that the product gamma lambda is equal to 0. They don't assume for the, indeed, no. For some of their main results, they need gamma to be non-decreasing, but not for all of them. I will explain that later. So this is the first model with varying infectivity and susceptibility. And the second one is a model with a vaccination policy. So this is a model I have introduced with Félix Foutel-Rodier and Arthur Charpentier. So R0 is defined in the same way. we have a curve of infectiousness and a curve of susceptibility, but we had some renewal process to model a vaccination policy. So at each event, one event can be an infection, a recovery, or a vaccination. So at each event, we sample new curves. So when there is an infection, we sample an infectious curve with compact support. And at the end of its support here, we will say that the individual is in the recovery state. We sample a first curve of susceptibility sigma 1, independently of the past. We also sample some vaccination time, first vaccination time, TV1. At that time, there is vaccination, so the susceptibility jumps from its value to 0. And we sample a new susceptibility curve, sigma 2, until, and we repeat this until the next infection. When the individual is infected, a new curve of infectiousness is sampled, and so on. So if I consider the susceptibility curve gamma, we can see that this is no more a non-decreasing function, because we have those random time of vaccination where the susceptibility jumps from its value to 0. So the assumptions are the following. The susceptibility is a bonding function with compact support. Sigma are non-decreasing function, so are random, with value between 0 and 1. And we have some independent time of vaccination, TV1, TV2, TV3, etc. TV is a typical derivation between two vaccinations. We assume that it's a L1 random variable independent of lambda and sigma. And the distribution of sigma is the same when it is from an infection and when it is from a vaccination. So this is the second model. And now the third one with Brizzotza. So R0 is always defined in the same way. But we work with a parametric model. It means that we will consider a family of curves, lambda and gamma, depending on some parameter theta. Theta belongs to some probability space, capital theta. So R0 can be written in such a way for a parametric model. The expectation is indeed the distribution of theta. So here at a new infection, at each new infection, we sample new curves of susceptibility and of infectiousness. But we have a memory of the last infection. So we introduce a memory kernel D, and at each new infection, so before the infection, I have some parameter theta, and at this time of for the individual, we sample a new parameter theta tilde, according to the memory kernel D, which so the distribution of theta tilde depends on the value of theta, so the previous parameter. And then the couple lambda and gamma will jump from their value with the parameter theta to their value with the parameter theta tilde. So we also assume that lambda is a bonding function with compact support and that the product gamma lambda is equal to 0. So now, have you some question about the models?
The function lambda must be integrable or not to have R0 finite.
Yes, I need this to be finite. Yes.
So it must be more than bounded.
Yes, more than bounded. Indeed, it is. So lambda is bounded with compact support.
Okay.
So the support, the length of the support should be L1.
Okay. Okay.
So our main questions will be the following. There are many questions in epidemiology, so I will focus on two main questions. Indeed, one main question, which is the long time behavior of the disease. So the two main questions related to that question is there an endemic equilibrium, and can we characterize it? And can we prove that there is convergence to disease-free equilibriums, which means that in the long time, the disease disappears? Or is there convergence to an endemic equilibrium, which means that in the long term, the disease remains in the population? So in the first model, Fourien, Pang, Pardue, and Brizotza prove that under this assumption, which is the limit when A goes to infinity of gamma is well defined, which is the case when gamma is a non-decreasing function. If R0 is smaller than this value, the expectation of 1 over gamma star, there is convergence to the disease-free equilibrium. So the disease disappears in the population. And when gamma is non-decreasing, so this is where they need this assumption. When R0 is strictly bigger than this expectation, there is existence of an endemic equilibrium. So we have this first result for the first model. Now for the second model with vaccination, we prove that, so I recall that if I consider the function gamma, gamma is indeed is defined from a renewal process, PV1, PV2, etc. So this is no more a non-decreasing function, but if each functional sigma are non-decreasing, there is existence of an endemic equilibrium if R0 is larger than this value, which depends on the vaccination time. So if we look at this formula, R0 is only defined from the disease. It depends only on lambda. So it depends on the disease only. But we can play on the vaccination time in order that this inequality cannot be true. And then if R0 is strictly smaller than this value, there is no endemic equilibrium. This is good for public health. So this is a way to have a good vaccination policy in our country. So this result in our article has been proved in some cases, but not in general. It was a conjecture in general, but with the new work with Brice, indeed, we have a proof in general for this result. And now for the third case, so the good assumption on the susceptibility is this one. So when the mean value of the susceptibility converge when B goes to infinity to some value gamma star, we can say that there exists an endemic equilibrium, even only if this integral is strictly smaller than 1, where sigma star is defined here. It is indeed the eigenfunction of some linear functional. I write it here. So I have a linear functional here, T, and sigma star is eigenfunction related to the eigenvalue 1. And we renormalize this eigenfunction such that this integral is equal to 1. So sigma star must satisfy those two assumptions. This is not nice. This is not a nice formula. It's quite ugly, I can say. But we will see later that indeed we recover the condition of the two first models. Now I will focus on the parametric model with memory. And I will explain more deeply how it works. So N is the size of the population. Initially, a proportion of the population is infectious, and each individual is described by two random processes. The first one, AI of t, is the age of the individual I at time t, which means it is the time since the last infection. And theta I is a threat of the individual at time t, which means that that is the value of its parameter. Consequently, the infectiousness of the individual I is just indeed the value of lambda at edge AI of t theta with threat theta I, and its susceptibility is the value of gamma at edge AI and threat theta I. And we introduce the empirical measure of threat and edges, and the global infection force of the disease in the mean value of the infectious over the population. So the individual I will be infected at time t at rate gamma I. Gamma I, it is its susceptibility times the force, the infection force of the disease. So we can see that if the individual I is already infected, gamma I is equal to 0 because we made this assumption. So it cannot be reinfected. It can be infected only when gamma I is strictly positive. And if it is, if this individual is infected at time t, its age will jump from its value to 0, and a new threat is sampled according to the distribution, the kernel D, which take into account the previous value of the threat. So D is a non-negative kernel with this assumption such that, because we want to have a probability distribution here. So the evolution, the behavior of the two processes can be described by some stochastic differential system where QI are independent Poisson measure. So this is the age and the threat of the individual I. And we can see that this couple of processes is a system of piecewise deterministic Markov processes. Indeed, the age of each individual grows linearly between two jumps, and the threat stays constant between two jumps. And these processes are in interaction through the force of infection of the disease, because this quantity here depends on the value of lambda for all the individuals in the population. So this is a stochastic description of the disease, but it's not easy to work with. It is too complicated. So one way to study the long-time behavior of the disease is to consider its deterministic limit in a large population. So we let n goes to infinity. And in the SIRS model, we can see that at the limit, the proportion of individual in the class S, I, and R are solution of some stochastic differential equation. And we can easily prove that if R0 is strictly bigger than 1, there is existence of an endemic equilibrium. And if R0 is smaller than 1, the disease disappears. In our case, the things are more complicated, but we can also prove such result using the propagation of chaos techniques. And we can prove that the empirical measure of edges and threats converge when the size of the population goes to infinity to a measure mu, which is defined by this equation. We recover here in this term R the jump. It models the jump effect at each infection. The edge jumps to 0 and the threat is changed. This is a nonlinear equation for mu because we have this dependence between, we have this term which depends on mu. If we assume that at the initial time mu0 as a density, we can prove that mu t has also a density, and its density is solution of this system of PD. And F here is indeed the limit of the infection force that I have defined before. When n goes to infinity, it is the infection force of the disease at the limit. So it depends on lambda and the density of individuals with edge A and parameter theta. So this system represents the distribution of edge and trait of a typical individual in a population of large size. And at the limit, we have PDs and not ODs as in the classical model, because the stochastic model is Markovian in edge. So we have partial derivative in time and in edge. So with Brice, we prove the existence and uniqueness of the solution of such a system. And now we would like to consider to study the equilibrium states. So an equilibrium state should satisfy the following equation. Indeed, at the equilibrium, the density does not depend on T, and the infection force does not depend on T. They are constant in T. So if I take the equation before, the derivative in T is equal to 0 at the equilibrium, and we can prove that there are two possible equilibria, of course, when the force of infection is equal to 0, the disease disappears, or an endemic equilibrium when the force of infection is strictly positive and the disease remains active. And we prove that if this limit exists, there is an endemic equilibrium when this integral is strictly smaller than 1, where sigma star is defined as I described it before. So this is not nice equation, but we can see that if I make some change of measure, I can call this measure P star. Indeed, I have to divide by the L1 norm of sigma star to have a probability measure, but if I consider this measure P star, we have exactly the same condition of existence of endemicity as in the first article of Forien, Pardoux, Pang, and Zotza. But we have just changed the measure. So up to a change of measure, we have the same condition of endemicity. So just to finish, when there is no memory, if there is no memory in the model, it means that this quantity D doesn't depend on its first variable. So we have just a D theta. There is something strange in my, I think I switched theta with theta tilde here. think theta tilde should be here. So when there is no memory of the past, this term depends only on theta tilde. And we can see that indeed sigma star is a constant. We have an integral term here. There is no theta. And sigma star is a constant. And with this, when sigma star is a constant, it doesn't depend on theta. And sigma star should satisfy this equation. Sigma star should be equal to 1 over the integral of lambda dA p d theta, which is indeed 1 over R0. So when there is no memory of the previous infection, sigma star is equal to 1 over R0. And if gamma is non-decreasing, we can prove that this limit is indeed the limit when b goes to infinity of gamma. And we recover the condition of endemicity of the article of Pang, Pardoux, Porien, and Zotza. And so I don't have any more time, so I just say that when there is no memory and we take into account a vaccination policy, we also recover exactly the condition we had with Arthur and Felix. So in this talk, I've presented a different stochastic model with varying infectivity and susceptibility. I made some link between them. I obtained a large law of number for those models and an endemicity criterion for the deterministic limits. So now the perspective for the model with memory is to study the convergence to the equilibrium. So there are two equilibriums, the disease-free equilibrium and the endemic equilibrium. And also study the case of heterogeneous population. Thank you.
Thank you for your Professor Hélène Guérin. Thank you for this nice talk. We start the questions. We start by a question from the public, from our colleague Marcel. He asks you, what about the case R0 equals 1? The question is, what about the case where R?
It's a critical case. Indeed, when for the classical model, we can observe that when R0 is equal to 1, we can have an endemic equilibrium. We really need R0 to be strictly smaller than 1. And what I wrote in my slides was not really correct. Where are my conditions? Sorry for... where is my condition? I can't find it. Too many slides. Okay. For example, this one, I said there is an endemic equilibrium if and only if R0 is strictly bigger than this value. This is not correct. There is an endemic equilibrium when R0 is strictly bigger than this value, and if R0 is strictly smaller than this value, we don't have an endemic equilibrium, but when R0 is equal to this value, I don't know.
Okay.
This is the critical case.
Okay. Okay. Thank you. The times TB1, TB2, and so on are IID times or not?
Yes. There are IDs.
So if I understand, the times between the moment of healing and infection are IID. I think that this condition is not realistic, no?
Can you repeat, please?
The time is TV1, TV2, and so on.
Yes.
Are IID.
Yes.
If we speak realistic, if we are infected, we have more chance to be not affected in the future. No? Yes or no?
In this TV1, TV2, TV3, etc.
Yes.
Are the time of vaccinations.
Okay.
This is just the times of vaccination.
Okay. There's no relation with
the disease.
With
no.
the disease. Okay.
No.
And the time is which separates the.
So
the
for
infection.
the COVID, for example, for the COVID, we say that we should be vaccinated every 6 months. I don't know exactly.
Okay.
So the first TV1 will be in 6 months, but as an individual, you won't go to make your shot of vaccination at the day we gave you. There will be some random.
Okay.
Some randomness.
Okay. And R0 is a Poisson process. Yes or no? R0.
R0?
Yes.
The critical value R0?
Yes.
No, it's a constant. It's deterministic. R0 is deterministic.
Okay. No, R0 is the mean of a Poisson process.
Yes, it is defined in this way.
The intensity, yes.
Okay, my question, why...
So it's a mean value of the infectiousness.
Okay, why use this notation every time? Why R0, it is not the integral of the expected value of lambda, dA. We can permit the integral and the expected value. Is the integral of expected value of lambda A. The same thing,
yes.
No? Yes. Okay.
It is the same thing. Yes, it is the same thing.
Everything is positive.
Yes.
Yes, exactly. So I can switch the integral and the expectation.
Okay. Yes, we said. Yes, please.
If you allow me, then your process here, gamma, has a special structure.
Yes, exactly.
Which looks like the Poisson shot noise. Whenever you take N as a normal Poisson process, the usage is to call it a Poisson shot noise. And the structure is very particular. There is some literature on it. I use it and face it this kind of processes.
Okay, but indeed, in our cases, TV is not always an exponential. Not always an exponential distribution. It can be something else. But just assume that the common distribution is in L1.
Right.
But we can have a gamma distribution or something else. So NA is not always a Poisson process.
Yes, I'm totally aware of this. And there are possibilities to approximate gamma of A for large A, at least when N is Poisson.
Yes.
And
yes.
N is whatever you want.
Indeed, I can compute my term of interest here, which was the limit of this quantity. And for a renewal process, we have exactly the good limit, the limit we had with the work with Arthur and Felix.
What I mean is that you can approximate the distribution of gamma A, not the integrals.
Oh, I don't know if I need it. If it is interesting to have but I can compute, yes, I can have information on its distribution, right? Yes, you're right.
If it's interesting for you, we can discuss this another time.
Maybe for a statistical point of view.
Estimate gamma A, you can have a kind of central limit theorem, a drift and
Yes.
and make this.
Yes, for a statistical point of view, if we want to estimate gamma, it should be interesting to have information on its distribution.
Mhm.
You're right.
Okay, in this slide, TV and sigma are independent or not?
Yes, they are independent. Indeed,
so-
sigma depends on the disease, and TV is public health policy. So we can't have a dependence between those two quantities.
Mhm. So the last limit can be simplified, no? It will be the integral between 0 and infinity, sigma A, the probability
The
that
last term
TV,
here,
last one, last line, last limit.
this
Last,
term here,
no, after,
no?
down, last line. Goes to expected, no, here. Goes to
Yes.
expected value of the integral between 0. This
Yes.
can be simplified to become integral between 0 and infinity. Expected value of sigma A, probability that to be less than A divided by, okay, just a simple remark. When the TV are exponentially distributed, are there
Yes.
some optimal value of the parameter of this exponential distribution to have an excellent situation? If you like.
We want this value to be um, large as possible. This is what we would like.
Okay.
And the best value of TB to have a large quantity is to take TV deterministic indeed.
Mm-hmm.
So when the government say you have to have a shot of vaccination every 6 months, you have to do it every 6 months, and it is the best. But nobody does that.
Okay.
May I interrupt you again?
Yes.
Because I find the correct reference for this kind of stuff. Would you allow me to share just one page?
Yeah.
We said.
So I stop my sharing.
Okay. You have a structure similar to this one, right? Maybe.
Yes.
Okay. And
yes.
It's
my night. Yes, it is my edge.
To under some technical exceptions to make this guy C is your processor to make this guy appropriately converge, normalize it, converge in a strong sense. Huh?
Mm-hmm. Okay.
Rescale
What
the
is
time, and you will have a limit theorem for processes. Huh?
Okay, but you have a scaling in time, right?
Okay. Then you modify the scale of time of your A. I stop sharing.
Okay.
Okay. Now you're going back to the slide. Sorry.
Okay, it is interesting. Thank you.
Are there other questions, please? Other questions? Okay, if not, we have to thank you again, Professor Guérin, for this nice talk.
Thank you.
And see you 13th February. Thank you, Professor.